Kevin Barth, and this is Gav's Gone, the Electric-Longboard project that I've been working on for a couple of years. It all started at IMTS, which is a machining trade show in Chicago in 2018, when the friendly chaps from Datron, who make beautiful CNC routers, gave me this aluminium deck, and they told me I could have it as long as I did something cool with it. So I said, sure, I'll make an electric longboard. Not knowing anything about electric longboards at the time, I thought I'd just wing it and see how I got on. So basically, what you see here is a bamboo enclosure. This was machined on a little desktop CNC router from a company called Vertigo Technologies. It houses a battery that I built with lithium-ion 18650 cells, and it's got some other control circuitry in it. Powers a brushless motor using vector control, and it's got a belt drive to the rear wheel. Now, the way this was designed, I used an off-the-shelf bracket to mount the motor, and it's never really been a great connection. You'll see what I mean if we look at it from the back angle. There's a slight angular misalignment on the belt, which means that the belt doesn't last very long. The first one shredded after about 200 kilometers. That brings me to the next part of the story, the generatively designed skateboard truck. As a member of the Autodesk Expert Elite program, we get access to some really cool technology like generative design from Fusion 360. This was something that I'd always been wanting to have a go at, so I decided I'd redesign the longboard truck with an integrated motor mount using generative design, just because I could, basically. I designed one and manufactured it on a 3-axis CNC machine, and the prototype looked okay, and I was about to run it on the board when I went to Autodesk University 2019 and happened to get chatting to John Saunders of Saunders Machine Works and NYC CNC. John took interest in the project and kindly offered to make a 5-axis version of the truck. So I went back to Fusion and reran the simulation with the 5-axis machining option and came up with this piece of geometry, which John has been kindly slaving away at for the last couple of weeks to build a beautiful 5-axis aluminium truck for me. Then last night I went back down to Vertigo and borrowed their 3-axis machine to manufacture a motor mount, and shortly this will be going onto the board. So for the next part of the video, I'm going to take you through some of the steps involved in setting up a generative design and then getting ready to manufacture it with CNC machining. As a starting point for a generative design project, you don't have to create all the geometry completely from scratch. In this case, I'm starting with a model of a Paris 180mm reverse kingpin truck that I found on GrabCAD from David DeLuca. And I've just used the hanger model because I measured it up and it was pretty accurate as a base for the structure that I want to create. So I'm just going to right click and isolate that hanger to show you what it looks like in its current form. Now I'm going to right click and export, and I'm going to save this out as hanger to my generative design project. Now that I've opened up the hanger component on its own, I can get to work removing the geometry that I want to replace with a structure that's been created by the algorithm. The first thing I'm going to do is remove any appearance overrides because I find that black quite hard to see the edges. So now that the hanger looks like the base material, I can just step through these features that I've created to show you the process. The first thing I do is create a work plane above the geometry. I then use the project tool to project geometry that I want to keep. I'm using the edges of these bosses as well as the pin at the top, and also the bushing seat.
From there, I just do a simple extrude cut down and remove all the material that I don't want. Then I can trim off the stub axles, as I'm going to replace those with machined stub axles that screw in. And now all I need to do is turn off the construction plane and the sketch, and then make a few quick model adjustments to extend the bosses slightly, add a flange for mounting the motor mount plate to, and then the interesting one is the bushing seat in the middle. So you'll notice that it has quite a thin section to it, and this won't allow much room or surface area for the material to attach. So I'm going to effectively thicken that up and just create a little rim which will provide a nice seat for the urethane bush to sit in, but also give it some more area to allow the growth to attach to. The generative design process needs some confinement boundaries to know where it's allowed to put material and where it shouldn't put material. I like to make the analogy to a company called Full Grown, and if you check out the website fullgrown.co.uk, you'll see an amazing process that they use to basically grow furniture. Now what they're doing there is they're training and constraining plant growth to basically form the shape that they're after. And generative design kind of works in a similar way. You can see here that I've got various bits of geometry that are nothing to do with the finished result. If I turn off the preserves for a minute, you can see all the red areas are areas where the algorithm is not allowed to place material. And if I turn off the avoids, you can see all the areas that I want to preserve. So we have to tell it where all these bits of geometry are and create any structures that we need to basically guide the material to where we need it. Here are a couple of tips for creating these boundary regions that might make creating the geometry a little bit easier. For this stub axle, I effectively want the inverse of that as an area where I don't want any material to attach. So I can do a project using the P key and then slice the graphics, create a circle that's somewhat larger than the boss, and then just extrude that whole cylinder as a new body. It can help to make that new body translucent, which you can do by changing the opacity. Now I can still see that it's there. Using the combine tool, I can remove the stub axle from that body that we've just created by using the cut option, and I'll tell it that I want to keep the tool because in this case the stub axle is my tool. You'll see now that if I turn off the stub axle, there's a cavity inside that body that's exactly the same volume as the stub axle itself. Another example is a cone that I want to avoid so that the kingpin can pivot as the truck rolls side to side. For that one, an easy technique is to project the top of the bushing seat and then use the extrude tool with a taper option, and now I can just define the angle that I want the kingpin to be able to tilt in and create that as a new body. Right, this is where the fun begins. We're going to switch over from the design workspace to the generative design workspace, and you'll notice that I've already got some previously created studies. Now there's quite a bit going on here, but effectively what we need to do is define all the conditions that we want generative design to take into account when it's designing our component. So the first thing I'm going to do is create a new generative study. You can see it's named it Study 4, and I've got 3 different types of geometry that it's looking for a start. Preserved geometry, as we mentioned earlier, is the bodies that you want to keep in the output. Obstacle geometry are the bodies that you want the algorithm to avoid when it's creating the geometry. And the starting shape is an optional shape that you can use to try and guide it further. So this is just simply a matter of editing the preserved geometry and then looking through the model components and finding the things that we want to keep. So you can see I've named these things to try and help me select them easier. I want to keep the pin, I want to keep the axle, the plate in the middle, and the axle on the other side. I can then click OK and do a similar thing for the obstacle geometry, where I pick the cones, the body that defines basically my ground clearance, the cylinders to protect the stub axles, a cylinder to protect the pin, and so on. I've also got a starting shape here, just as an example, if I want to make sure that it doesn't grow outside that box. Then I can choose starting shape and select that as well. So you'll notice that it's colored the various areas different colors. So that's all I need to do for the geometry section. The next thing to do is to start to define the objectives of this study. If I expand out objectives for study 4, you can see that the current target is to minimize mass. Up on the ribbon, the objectives button allows me to choose whether my target is to minimize mass or maximize stiffness. And you'll see with minimize mass I can specify a safety factor. Maximize stiffness gives me an additional mass target, so it will attempt to work as close as it can to that mass target while still maintaining your safety factor. So in this case, let's just see how strong we can make it while staying above 500 grams. The next thing to do is to define the materials and the manufacturing method. So under manufacturing, you'll see that at the moment it's set to use unrestricted, additive, and milling. If I edit this, you'll see that it can take into account a number of different variables, including production volume. I'd love to have to make 2,500 of these things, but realistically, I'm probably only going to make 2 or 3. Unrestricted is a bit too free for me. I don't have access to all the manufacturing methods in the world. And in fact, for this study, I don't even have access to 3D printing. So all I'm really interested in is milling. You'll see down the bottom, 2-axis cutting and die casting are also options. But under milling, I want to use 5-axis. 5-axis opens up a whole lot more opportunity for shape because it allows the tool to get into areas that it wouldn't otherwise be able to access. You'll see that there are some additional properties for specifying things like the tool diameter, the stick out, and the diameter of the collet or tool holder that you're using. And it takes all of these parameters into account when it's trying to figure out where it can position geometry. This is the true magic of this generative design implementation, is the fact that it can take manufacturing into account and not generate nonsense geometry that's impossible to manufacture. Now we have potentially the hardest part, defining the load cases. I found that I get best results when I define multiple load cases. So rather than trying to put in all the forces and constraints that I want on the part, I think about them as separate cases and the algorithm will take all of them into account. It works a lot like an FEA or a finite element analysis study. You can define constraints, which are where the component is restrained from movement, and you can define loads, things like forces and pressures and torques. Now a bit of a disclaimer here. While I have a working understanding of engineering mechanics, I'm by no means an analyst. So I don't claim that these loads and conditions that I'm about to show you are super accurate or even valid. They're just my best guess and they were a starting point to create some geometry. So to be honest, I am a little bit scared about riding this thing because if I've got the load cases wrong, I might end up on the ground. So after trying various load conditions and looking at the results, I basically settled on this load case here as the one that we finally produced, which I call ground clearance, because I put some obstacle geometry in to make sure that I maintain good ground clearance. Now you can see that I've got 3 load cases: static, motor torque one way, and motor torque the other way. After talking to some guys on the eSkate forums, we came to the conclusion that while the motor doesn't directly apply torque to the axle because the wheel can rotate, under acceleration and braking, the force on the motor mount induces a torque on this flange. So I've called it motor torque because it is the torque generated from the motor mount. So you can see I've placed a moment load on that cylinder. I've pinned the top pivot and fixed the bushing seat. I've then done the opposite for the reverse direction. One for acceleration, one for braking. And the static load, rather than putting forces on the axles and restraining the bushing seat and pin, I decided to flip it upside down and basically apply the force to the bushing seat in the vertical direction and then pin the top pivot and put frictionless constraints on the little flats on the axles. The reason for these frictionless constraints is they mean that while the axles can't move up and down, they can move in any direction. So this is sort of allowing for some slip, I suppose, in the tires. Now I haven't taken into account angled loads leaning on one side or the other. So to counteract this, I've just gone for higher safety factors and higher loads than I think are necessary, and I've treated it as if all the load is on one truck rather than on 2, which might be the case if I was sort of leaning really hard on the back or went over, a stone. People I know that work in transport have told me that they often use what they call a 2G bump load, where they basically simulate twice the acceleration due to gravity on the load as a sort of general case for driving around on roads. And so I've gone a little bit more than that. To create these loads and constraints, like most other things in Fusion, there's a nice user interface. You can see up here I have structural constraints and structural loads. If I click on structural constraints, I've got some various types: fixed, pin, and frictionless. And with fixed, I can choose releases in different directions. So if I wanted to fix that cylindrical surface, I can choose which axes it's fixed on. So this gives me some flexibility. I mentioned frictionless before for allowing a surface to slide, and then we've got pinned as well. And pinned also has the ability to release directions. So in this case, by releasing the tangential direction, it allows the pin to rotate, but it's still fixed radially and axially. With the loads, we've got forces, pressures, moments, and bearing loads. I did consider using bearing loads and actually simulating effectively the contact with the bearing on the axle, but decided against it and tried to simplify it a bit more. For any of these, you can pick a surface, you can adjust angles, and you can specify a magnitude for the force. It's a really nice to use interface and easy to create reasonably complex loads quite quickly. So all that's left to do is to choose some materials for our study. You can just drag them up into the top. We can run a quick pre-check. Now we can see that there's some issues here with some of our simulations. The study that I want to run though, the ground clearance study, looks like it's okay. So after turning off any geometry that will get in the way of the result, I can use the previewer to get a rough idea of the shape that may be created. This can take a little while, so I'll speed this part of the video up. So it looks like it's heading in the right direction, so I'm going to stop it there, then hit generate, And now we wait. Now in my experience this can take anywhere from a few hours to a couple of days, depends on how many different variables you give it, but the beauty of the process is that it's generating multiple outcomes at once. So rather than sit here and wait, we'll skip ahead to show you what the outcomes look like. So this is the workspace for exploring the generative design outcomes. You can see that there are multiple results here. Some of these are where I've specified more than one material for a particular set of conditions, but it can also be where I've specified multiple manufacturing methods. But now I can basically go through and using various displays and filters, I can compare all of these results and find the one that most suits my needs. Now after reviewing these and sort of looking at a number of different factors including manufacturability, the one that I ended up choosing was this one here, the ground clearance one. So this was iteration 29 that ended up working, and you can actually go back and you can look at previous iterations. So if there is some material that's broken through that you're not quite happy with, you can step back and look at maybe a more simplified version. So you can see how this design evolved over time, and it's quite fascinating to have a look and sort of see how this generative algorithm is coming to the result. Once you've chosen one that you're happy with, you can then export it in a few different ways. There's two different options, the mesh design and what they call design, but it's actually a T-splines body. If I click that, it will charge me some more cloud credits on top of what it charged to do the generative design process to download the model file. You can see that this one has already been generated, so if I click open, it will just open the existing one. Now the great thing about this model is that this is based on a T-splines body, and T-splines is a really nice manipulable sort of fabric to adjust and refine the design. You can see that there's areas of imperfections and things that we might not be happy with. Now if this had just generated a mesh body, there'd be very little I can do, but I can do things like patch holes or simply just delete faces that are unnecessary to try and tidy this up a bit. Now T-splines editing is a whole topic in itself, but you'll see that the body is actually made up of a T-splines body as well as our preserve regions that we started with. So as long as you make sure that the T-splines body always intersects those preserve regions, it will be able to calculate this entire volume. This means you can go back in your timeline and you can edit the T-splines body, and you can start to use the manipulation tools to adjust this geometry slightly. And there's all sorts of things that you can do in this mode that allow you to really refine the design. So in the design I chose, I didn't really like the look of all the rounded edges on the front, on the nose here. So I spent quite a bit of time adjusting these points to get nice beveled edges, and you'll see those in the close-ups of the model later. Now we come to what in some ways is the most exciting part, where we generate the CAM toolpaths to actually bring this thing to life on a CNC machine. So this is the work holding setup that John gave me that he wanted to use on his machine, and I set it up in Fusion initially with a rectangular block of stock sticking straight up. I was having some problems with access, and John had the bright idea to actually cut the stock off at an angle, tilt it over, gives us slightly better rigidity and gives us a lot more access in around the nose and that complicated geometry. So that was a great brainwave. You can see that I've just got one setup here. The finished part ended up being two setups, and John built a clever fixture to do the finishing for the last side. So you can see I split it up into prep, roughing and finishing, and I'll do a quick simulation of the whole lot so you can get an idea of how much detail went into these toolpaths. As you can see there, we needed some long tools, some long extensions, some crazy angles, and reach into all kinds of nooks and crannies. It was a really awkward and challenging part to program. A reasonably recent addition to Fusion 360 is the Advanced Manufacturing extension, which you can purchase per month with cloud credits. There are a bunch of really useful tools inside it for probing and automatic hole recognition for cam and things like that. But what was particularly useful for me here was the 5-axis collision avoidance and the steep and shallow strategy that users of Power Mill would be familiar with. The steep and shallow strategy can automatically tilt the tool axis to gain access into really hard to reach surfaces on the part. And this, while it takes a lot of time to get right in the programming and it takes a long time to simulate, it creates a really nice toolpath at the end of it, which gives a nice even surface finish. Because of the complexity of the job and the sheer number of toolpaths involved, I found that it was taking a really long time to generate the toolpaths when I made changes. So the workflow that I adopted was to lock things down using the protect option on the toolpath once I was happy with them. And so I'd only be generating the new toolpath that I was working on as I went along. And this saved a bit of time. All in all, many hours, nights and weekends were spent getting that program to the point that I was ready to hand it over to John, and he was then able to run that through Complete and find issues with it, and after further refining it himself and doing the last operation for the second setup, we ended up with a fantastic looking result. So now it's out with the old and in with the new. This has been an amazing project and I've got to work with some really cool people. I can't wait to ride this board with the new Generative Design truck, and I just hope it holds up. I'd like to just say a massive thanks to John Saunders from NYC CNC and Saunders Machine Works. Without him I'd still be stuck with the 3-axis version. Brett Cottle from Vertigo Technologies has been a huge help letting me use his machine and all his facilities to build cool parts. CAD Pro Systems, my employer, for always supporting me to do all these cool projects, and the Autodesk Expert Elite program for the amazing software they give us access to and the great community that they support.
You might be wondering why you haven't seen the finished product yet. I've got to admit, I goofed and sent John the wrong thread spec for the stub axles. Luckily, Jason Sutherland from MJ Custom Engineering was more than happy to help out and machined some overnight for me and got them down. So here it is, the final result.